Welcome to the lecture 13 of week 5 of course Climate Change and Extreme Events. In the previous lecture, we have talked about different types of probability density functions, distribution functions. We have also discussed about what is their differences, which type of distributions are used in which types of applications, for example. Then we have also talked about extreme value theory application, these distributions, extreme value analysis. We have talked about uh, POT, peak over threshold method, and then we have also talked about block maxima approach, annual maximum series approach. Then we have also talked about GEV or GPT type distributions and their application. And towards the end of the week 4, we have also talked about how do we use real-time data set to fit these distribution and to identify the what is the pattern has been changed over the past decades. In this lecture, we will primarily focus on the time series. So when you collect the data, if the data is coming from, let's say, some sort of observed stations, or let's say it is coming from satellite remote sensing, or it is coming from some sort of reanalysis product. So there are two types of data set. One is your spatial data, where we have information of each different points, or we have a time series data, where we have in one point you have multiple time of the data set. Let's say each of the monthly you have rainfall data, or you are measuring, let's say, rainfall amount daily, or you measuring rainfall amount sub daily or hourly basis. Then let's say if you are measuring this information for a very long period of time, 10 years, 20 years, like that. So you can make some sort of time series where you have certain low values, then high values, low values, high values, and the values will be fluctuating in that domain. That is called simply a time series data set, where you look at particularly what is the trend of the data, whether your data set at one particular point is increasing or decreasing, or whether it is more or less constant. What is the seasonal pattern? So uh, every year monsoon comes in June month, and then JJAS month is your called as a monsoonal month. In this period, it is like you have higher rainfall. Then after that or before this period, you have very low amount of rainfall. So this is a kind of seasonal pattern. So let's say if you are measuring rainfall in those regions where monsoon dominates, you will have some sort of seasonal rainfall information, where you have pre-monsoon month you have low rainfall, and monsoon month you have higher rainfall, post-monsoon month relatively lower rainfall, like that. So this is called a kind of a seasonal pattern in the time series. That is also very important to assess whether a seasonal behavior has been throughout the time is stationary, or it has been also changed because of some stressors or some sort of climate change effect, human activity effect, like that. Then you also important to assess what is the stationarity of the data, whether the statistical property of entire time duration is consistent, or let's say if you divide the data set in two parts, and if there is some sort of jump in the data, there you will see that there is a statistical change in the probability distribution functions. Or let's say if you have two different types of time series data, so how do we make some sort of correlation, whether let's say rainfall and runoff, let's say rainfall and temperature, these two data set time series are correlated with each other. What is their correlation, whether it is positively correlated, whether it is negatively correlated, or whether it is no correlation at all. So these kind of analysis is very, very important and essential when we are looking at the overall dynamic behavior which has been changed temporally in some sort of time series data set. That is what we are going to discuss in this particular lecture. So in the what would be the learning objective of this lecture is, we will define the key concept in the time series analysis. We will explore the methods to detect trends and seasonality. We will also understand what is the stationarity and its implications. And we will also look at how to measure, let's say, correlation in the time series data set, what is their importance of correlation in the data set and its applications. So what is time series analysis? So you have essentially a time, data points at different time interval, a definite time interval, and then you basically plot the data and then look at the data whether the data has any kind of change in the behavior or whether it is more like fluctuating in nature or stationary over the time. So this is kind of a simple explanation of time series analysis where you analyze the data points collected at successive time intervals. What is their relevance in the climate science? Because when you have the time series data, you can look at the, let's say, temperature trends. You can look at the precipitation cycle, precipitation trends. You can also look at atmospheric or weather related meteorological variable or their behavior over the past few years or decades, like that. So what is the key components of time series analysis? Essentially, we will look at the trends of the data. We look at the stationarity of the data, whether the statistical properties are consistent. Then we will look at seasonal pattern, and we also look at the correlation of different types of data set. So suppose you have suppose you have different types of time series. For example, this time series shows a kind of a linear trend where it is increasing over the time period. This is a example time series where it shows that so the behavior of the time series is sort of seasonal. So every 2-3 months it has higher and lower peaks, like that. And this pattern is repetitive if you look at entire time series. So this is a sort of seasonal behavior of our time series. This is another seasonal behavior. This is cyclicity of the data set where you have general cyclic pattern where you have higher and lower, and within that you have increasing and decreasing trends of the data set. Or you have, maybe you can also have the data set which is irregular in nature, whether we don't have any definite trend or sort of seasonality or cyclicity behavior in the data set. So that is called irregular or random behavior of the time series. So one of the most important concept in the time series is called trend analysis, quantifying trends in time series. So why it is important? Because if you look at any data, let's say if you look at CO2 rise data, you will see that there is a consistent increment of CO2 over the past few decades, which means there is some sort of linear trend. Or linear trend means there is a slope or linear rate of increment of the data set. That is called sort of the trends in the data. Similarly, you can also have multiple other variables which can show that decreasing trend, or that you can plot a linear relationship and can calculate the slope that will tell you about what is the rate of decrement of the data set. So when you have try to assess the trends in the time series, there are three methods which can give you an information about whether the trend of the data set is increasing, decreasing, or fluctuating. So you can use the moving averages. Moving averages sort of window where you calculate the average values of each different data points, and you plot it at the same plot, where you will get that what is the smooth behavior of your data set. What is their major thing? Basically it smooths the short-term fluctuation and it highlights your long-term trends in the data set. Then another type of the analysis is called linear regression. So linear regression is basically you have to fit a line in your data. If let's say if there is a this kind of the data set, if I fit a line here, it tells that the rainfall is consistently increasing according to this particular line. However, when you look at the data, it shows that there is some sort of very high increment event and then very low decrement event. Within that, this particular trend analysis or linear regressions are averaging those higher fluctuations and fitting a particular line in between of the data set. So that is called linear regression. Then another test is called Mann-Kendall test. Mann-Kendall test is very important test, which is a non-parametric statistical test, which means it does not assume any kind of probability distributions prior to application of this test in the mod data set. And therefore it is called non-parametric statistical test. It is basically used to detect the monotonic trends without assuming normality or normal distribution assumptions. So this test basically tell you about whether in your data set there is a trend is present or not, and if the trend is present, whether this trend is statistically significant or insignificant. When your value of p is, let's say, less than 0.05, which means at 95% confidence interval you are sure that the trend present in your dataset is statistically significant. If the trend of the dataset is not, the p value is not less than 0.05, then you may not be very sure about the trend is present. However, the statistically you cannot prove it. So that is what exactly the Man-Kendall test basically tells about the dataset. It basically check whether the trend is there or not, plus if the trend is present, whether this is statistically significant or not, like that. So here you can see two examples where Man-Kendall has test has applied, and they basically you can see that linear regressions or linear line of the trend, where you can see that either this is increasing or it is kind of a decreasing trend, like that. Then the another analysis in the time series is called seasonality, which is basically defined by periodic patterns occurring at a regular interval, annual rainfall cycles, monthly rainfall, or monsoonal or pre-monsoonal rainfall behavior or temperature behavior, like that, or winter or summer temperature fluctuations. That is basically called some sort of seasonal pattern. So there are methods which basically can be used to decompose or demystify these seasonal pattern from the time series. First is called Fourier transformation. So Fourier transformation is a kind of a method which basically used to, if you have time series data, the Fourier transformation can transform your time series dataset into your frequency domain, and with the frequency domain you can basically highlight which of the frequency is prominent and which of the frequency is considered to be as a noise. So that is what Fourier transformation is helpful, and it is also helpful because it can detect the most prominent seasonal pattern in your dataset. Seasonal decomposition of time series, STL, which is also a very important concept, where basically it uses the let's say if you have a time series dataset which can use to declutter the trend or seasonal pattern, or let's say some sort of fluctuations or residuals or noise in the dataset. So that is called decomposition of time series dataset. Then another important analysis when we are detecting the seasonality is autocorrelation function. So suppose you have rainfall data at a monthly time period for a particular location. Or let's say you are interested in whether the rainfall of June month is how the June month, or let's say T-1, a month, 1 month before rainfall, how it is basically correlated with your the present month rainfall. Which means you have a rainfall time series and you have to just shift your time series into T-1. Then you have another time series, and you, based on these two time series, you can basically done some sort of correlations. So whether you have higher correlation, lower correlations, like that. Similarly, you can apply this algorithm, this whole analysis for multiple lags. You can do T-1, T-2, T-3, T-4, and T-n, like that. So this way you can have the axis where you have lag information with your correlations, and that graph will tell you about what is the autocorrelation in your dataset when you are taking multiple lags within your dataset. So this is how basically you can detect the seasonal pattern from your dataset. The another important concept is called understanding the stationarity. So as the beginning we have discussed about, when you are talking about stationarity is the when you are looking at the time series, you are looking at whether the statistical properties of the time series is consistent or not. So stationarity is the behavior which tells you about statistical properties. For example, mean variance remain constant over time. Why this matters? Because many statistical or ML models assume stationarity for accurate forecasting. So when you are using some sort of statistical analysis, let's say frequency analysis, or let's say another types of analysis, so where you are interested in the time series should be in your stationary conditions. It should not have the non-stationary component. so that we can fit the model, or we can predict it for future conditions, or let's say for some sort of fitting into the some sort of probability distribution functions like that. How do we check the stationarity? There is a two method which is called augmented Dickney and Fuller test, ADF, or there is a KPSS test. So these are the tests where it tells you about if it is gives you certain probability numbers. With that numbers, you can basically look at whether your data set is stationary or non-stationary in the behavior. So there are methods which are basically, let's suppose if you have using the time series dataset and you get the dataset is non-stationary in the nature. How do we deal with that? So there is a very basic approach is you can take differencing t minus 1 and t. If you take these two difference and make another time series, that would be kind of can remove the non-stationarity component in the data set and can make your data as a stationary. Or maybe you can take log transformation, log 10 natural log transformation, and that will also make your time series stationary one. So this is the sum of the non-stationary time series data set. For example, here if you look at there is a consistent mean. However, when you look at the variance over the time, it is basically decreasing. Therefore, statistical properties are decreasing. Here it is basically the means are consistently increasing and variability is remain same. Therefore, the statistical properties is changed over the time, and therefore it is considered to be as a non-stationary time series. Here also you can see there is a time series with constant mean, constant variance, but non-constant covariance. Therefore, you can have a different behavior of the time series can be considered as a non-stationary data set. Then there is another concept is called correlation in the time series. So for example, it measures the relationship between two or more time dependent variable. There is a one example of correlation is called autocorrelations, where we are correlating the time series with lagged version of itself, or cross correlations or relationship between two different time series. Let's say rainfall or runoff, rainfall or temperature, rainfall or soil moisture, like that. Or autocorrelation basically we use only for single variable. Let's say rainfall t time series and rainfall t minus 1 time series, like that. And then we make it two different variable, and then we do some sort of correlation analysis. So here is one of the examples. So when you are dealing with the correlations, we can either use Pearson correlation coefficient or Spearman correlation, and then you can use it for their strength or weakness, or negatively or positively correlations between different types of variables. These are the lag plots, where if you take a single variable and you do some sort of lagged version of the time series t minus 1, t minus 2, t minus 3, and t minus n, like that, you will get some sort of, this is kind of auto correlation or cross correlation coefficient between different properties. So this is how basically you can correlate with rainfall and mean temperature, rainfall and vapor pressure, and vapor pressure with your relative humidity, and then you can find out which lag at which period or for what variable you are getting the highest correlation within the data set. Once you get this information, you can basically look at the processes and you can interpret whether what kind of the processes is dominating. Then one important concept in time series is decomposing the time series data set. So decomposing, let's say you have trends, you have seasonality, you have some sort of random noise. So what is important thing is you have to figure it out, what is the trend in the data, what is the seasonal behavior in the data set, and what is your random noise present in the data set. So when you decompose your time series into multiple part, you will have a better understanding about the trend, seasonality, and the random noise. And then you can also build some sort of additive or multiplicative model to predict it for future, or let's say within the time series conditions. Additive models are when you are adding all these four component, or multiplicative models are when you are multiplying these different component from the time series. So this is basically essential, is very essential, where you are looking at how the time series is behaving over the time period, and let's say which trend or seasonal behavior or random fluctuation are dominating. Then in another important concept in time series called time series smoothing technique. What is this? Basically, when you have, let's say, multiple fluctuating values. Let's say this is your mean temperature anomalies from 1980 till 2020 or after that. So basically you have some sort of increasing trend, you can look at it. So basically what we do, we basically apply moving averages. Moving averages calculate the average of fixed number of consecutive observations to smooth out variations. For example, here we can take 5 points window or year window like that, and then you can take average values of these 5 year windows, and then you can plot along with this data set along this plot, and you will see that whether your data of your temperature anomalies are consistent or whether it is increasing. So when you fitted the moving average in this time series, you will see that since 1880 till 1960 or beyond, let's say 1970 like that, this data set is more or less consistent or fluctuating, as not rapidly increasing. But if you look at since 1970 till beyond 2020, you see there is an exponential rise in the temperature data set, which means that temperature is significantly increasing, and which is basically clearly shown by these kind of smoothing techniques or moving average techniques. There is another technique, exponential smoothing can be also done when you have exponentially decreasing weights to the past observations, and that basically can be applied when you have recent data set and you wanted to give them more weightage compared to the historical observations. Then there is another concept in application in the climate science when you are talking about time series is correlations. For example, if you look at this plot here, it shows that there is a one property X and there is another property Y. Then there is a, when you correlate these two variables, which shows that either your variables are positively correlated, or whether these variables are negatively correlated, or whether there is no correlation at all. So what do you mean by positive correlation? Which means when you increase one variable value, the another variable value will also increase over the that scatter plot, and therefore it is a kind of a one-to-one relationship, or it falls out in one-to-one line or very close to the one-to-one line like that. So this is called positive correlations. When you assuming that negative correlation, which means when the one variable is increasing, another variable is decreasing over that particular line, and therefore it is a sort of negative correlations relationship. And if there is no correlation at all, that will show some sort of random fluctuations. What is their applications? Let's say if you are interested in what is the role of temperature trends on CO2 rise or global GHG rise, you can take some sort of one-to-one correlations between temperature anomaly or CO2 concentration like that, and you can look at it whether your data set is showing some sort of positive correlation, negative correlation, or no correlation at all. You can also look at precipitation cycle, studying seasonal monsoonal behavior, or let's say what kind of stressors are influencing the seasonal monsoon amount because of changing pattern. That can be also done by creating some sort of correlation data set. Or maybe you can look at some sort of ENSO event or regional. What is ENSO effect on, let's say, extreme precipitation? What is the ENSO effect on, let's say, low amount of precipitation? What is the ENSO effect on higher temperature rise? So one-to-one correlation you can develop, and then you can look at it whether large scale processes has any correlation with your smaller scale processes, or let's say regional meteorological or weather extreme patterns or rainfall patterns or temperature patterns. That is what we can do using some sort of correlation analysis. Now the important question is which tool we should use when we are using the time series analysis. Of course, you can use multiple programming languages, which can be Python or MATLAB. There are several toolbox available. For example, in Python you can explore pandas, stats models, scipy, matplotlib, or in R you can use forecast or t-series or ggplot2, or MATLAB. There is a dedicated tool, time series exploration and analysis, that can be used to get a very very insightful information from the time series by, let's say, decomposing into different component, or doing the trend analysis, or let's say correlating with multiple different variables, multivariate analysis or bivariate analysis, or let's say you are interested in what is their autocorrelations or lagged version of the time series, how the memory component dominates in the time series, like that. That can also be done using these types of softwares. There is some case studies where it shows that what is the application of these time series dataset. For example, you can look at long-term temperature trends in the Arctic Sea. You can correlate with in this paper they have correlated with some sort of different pattern, this difference from average temperature degree, and these are the temperature pattern they have done, and then look at how the temperature is increasing or decreasing, or what is the linear trend in different in this part of the world, like that. In the case study 2, they have worked on seasonal variability in Indian monsoon, whether is there any change in your seasonal variability, which is basically originated from different climate models, and how it has been observed, let's say pre 2000 period and post 2000 periods. And they have also tried to look at the trend analysis at different points where you have some sort of increasing or decreasing trend of your rainfall or some other parameters, like that. Then there is a case study 3 where people have looked at the correlation between ocean temperature and hurricane frequency. You can look at it whenever you have higher temperature, the hurricane frequency has been increased, which is kind of showing that one-to-one correlation between the temperature of ocean and the hurricane intensity, and which can gives you a clue about whether these two processes are somehow linked with each other. Then it basically you can explore about how these two processes are linked with each other, like that. So these are the case studies where we basically use the simple concept of time series, and then we can try to understand about how the time series are behaving historically, what kind of the variables are influencing the one particular variable, or let's say multivariate rainfall analysis, or multivariate analysis of time series, or let's say doing some sort of seasonal or frequency, or let's say understanding about seasonal pattern in the time series, like that. What is the challenges in time series analysis is, let's say when you have time series data set, it has to be non-missing values, which means if there is a missing values or gaps, that might create some sort of problems. However, there are approaches there which can be used to fill those gaps and can do that analysis. Therefore, when you have missing values, you have to be very careful because missing values means there is a loss of information, and you need to have some sort of expert advice or some sort of expert tools which needs to be implemented before doing some sort of time series analysis. Non-linearity, it is possible that you have a non-linear pattern in the data set, and therefore you have very different results compared to when you are understanding the or fitting only the linear model in the data set. Or it is might possible that complex climate interactions. So for example, there are conditions called compound interactions, compound events. So there are multiple events are happening at the same time and influencing one particular variable. Let's say in that scenario, when you are only looking at that variable with only one variable, it might possible that you miss that the complex interaction. You are only finding one-to-one correlation between two variables. However, it is not a two variable case. It is basically multiple processes at the same time are governing these changes. Therefore, complex climate interaction is one of the important area of when we are doing the time series analysis. The another part is long-term dependence or climate processes with memory effects. Basically, when you are dealing with some sort of lagged data set, it is very important to look at those lagged behavior, because when you are dealing with some sort of hydrological time series, climatological time series, there is some sort of memory terms involved in the time series, which has a kind of temporal memory pattern, where you have some sort of memory which basically transfer after one step to the another step. That is basically we have to take it into account when we are also dealing with our time series data set. That is one of the important part. So these are the some of the tools, some of the which we have already discussed, the tools, some of the books which are very useful dealing with, let's say, application of the time series using R, application of the time series using Python, or some sort of very basic or advanced, statistical analysis of time series, you can look at it and you can read these books, or also you can go through all these links where you will get multiple insights about different types of time series dataset. So in the next lecture, we will talk about detection of changes in extreme events and their properties. Thank you very much for your attention.